Welcome to this NPTEL lectures on robotics, basic and advanced concepts. In this week, there will be 3 lectures. The first lecture deals with mathematical preliminaries required to model and analyze robots. It will also include the very important notion of something called homogeneous transformation matrix. In the second lecture, we'll look at how to model and represent joints and links of a robot. And in the third lecture, we'll look at examples of DH parameters and link transformation matrices. So the first lecture is on mathematical preliminaries. So what do we need to know, or how do we proceed? So we recognize, or as mentioned earlier, the links of a robot will be assumed to be rigid bodies. Okay, so the first important thing that we need to understand is how do we represent the rigid body which models the links of a robot. So to represent a rigid body in 3D space, we look at the position and orientation of the rigid body. To represent the position of a rigid body, basically we need a right-handed coordinate system to start with. We need a reference coordinate system. Okay, a reference coordinate system or any right-handed coordinate system is specified by an origin OA, x-axis, y-axis, and z-axis. We are going to use several coordinate systems, so we will keep track of by labeling the coordinate system with A, B, and so on. So in this case, we have an XA axis, a YA axis, a ZA axis, and an origin OA. So the rigid body is represented by potato-shaped contour. Okay. So the right-handed coordinate system is specified by an origin OA, a set of 3 mutually orthogonal axes, unit vectors XA, YA, and ZA. You can think of these along the index finger, the middle finger, and the thumb of the right hand respectively. And as mentioned, we will label each coordinate system, and in this case it is labeled as curly bracket A. Okay, so as I said, we want to represent the position of a rigid body in 3D space. So the first natural question is position of what? So basically we want to find the position of a point of interest on the rigid body. And what could be the point of interest? It could be, say, the center of mass or the center of gravity, or even maybe location of a sensor or some special point on the rigid body. So this point P, which is shown in this figure, can be represented using a vector drawn from the origin OA to that point. And we are going to keep track of in which coordinate system this vector is shown by this superscript, leading superscript A. Okay, so this vector AP can be represented using 3 Cartesian coordinates, Px, Py, Pz. So this is a column vector. So Px, Py, Pz transpose means it's a column vector. So what are these Px, Py, Pz? They are nothing but the projection of this vector AP along the XA axis, YA axis, and ZA axis. So this AP can be written as Px into XA, Py into YA, plus Pz into ZA. XA axis is nothing but 1, 0, 0 as a column vector. YA axis is 0, 1, 0, and ZA axis is 0, 0, 1. So hence AP is nothing but Px, Py, Pz as a column vector. So the position of one point on the rigid body is not enough to describe it in 3D space. So you can think of let's say you are holding a cube. Okay. So if I give you the corner of the cube, that is not enough, because based from that one point, which is the corner of the cube, I can rotate the cube about some different directions. Okay. And it will look very different to different people when you rotate it. So the moral of the story is the position of one point on the rigid body is not enough to describe it in 3D space. we need something called as the orientation of a rigid body with respect to the reference coordinate system. Okay, so how do we describe the orientation of a rigid body B? So first is we attach a coordinate system B to the rigid body B. So this is the rigid body B. So we have a reference coordinate system XA, YA, ZA and an origin OA. We attach another coordinate system XB, YB, ZB with the origin OB, okay, on the rigid body. Now we are only interested in the orientation right now, not in the translation. We'll come to that later. So then the origin of OA and OB can be at the same place. So if I can describe to you or specify to you the XB axis, the YB axis and the ZB axis with respect to the A coordinate system, or another way of saying, if I can describe the coordinate system B with respect to A, then I could very completely describe the orientation of the rigid body in A. Okay, so again the example of a cube, if I tell you that the three edges of the cube, let's say labeled as X, Y and Z, if I tell you which way or how to draw this axis on the cube, then completely describes the orientation of the cube. Okay, so in this figure I am also showing some vector k and phi. We'll come to this later. Okay, so remember there is an axis k and an angle phi on the rigid body, which is useful to represent the orientation of the rigid body. So let's proceed. So the unit vectors xb, yb and zb are attached to the body B, and they can be described in the A coordinate system just like the position vector of point P in A coordinate system. So xp is nothing but the point P. So it can be written in terms of xa, ya, za. So project this xb vector, unit vector, okay, along xa, ya, za, and call the coordinates as r11, r21, r31. Okay, so what are we doing? So we take a point 1 unit away along the xb axis. So this is the vector axb. We project on xa, we project on ya, and we project on za. And when we project, the coordinates are r11, r21, r31. Okay. So why is it written in r11, r21, r31? Basically, axb is a column vector. Okay, so r11 into 100, r21 into 010, r31 into 001. So it will form a column vector. Likewise, I can take a point on the YB axis 1 unit away from the origin and again project onto XA, YA, ZA axis, and let's call the coordinates r12, r22 and r32. Okay, and finally we can also take a point on the ZB axis 1 unit away and project onto XA axis, YA axis, ZA axis, and the coordinates are r13, r23, r33. Okay, so these Rij's are called the direction cosines. You must have heard of this before, but let's see why are they called direction cosines. So let's compute what is r11. So how do I compute r11? So we take this first equation and dot product the left and the right side with xa. So axb dot xa will be nothing but magnitude of axb, magnitude of xa, and the cosine of the angle between axb and xa. Okay, so since these are unit vectors, we are only left with the cosine of the angle between axb and xa. Okay, and this is r11. So r11 is nothing but cosine of an angle between two axes in 3D space. So we can define this 3 by 3 matrix containing Rij, and this is called as a rotation matrix. Okay, so there are 9 elements: R11, R21, R31 first column, R12, R22, R32 second column, R13, R23, R33 third column. Okay, and this is again repeated again. So the first column of this rotation matrix is R11, R21, R31, and it is the same as the AXB vector. Okay, so effectively, what is this matrix ABR? It is first column is AXB, second column is AYB, and the third column is AZB. Okay, so what does this ABR means? It is the rotation matrix, okay, describing the rigid body B with respect to the reference coordinate system A. Okay, so ABR completely describes all the three coordinate axes of B with respect to A, because if I know this rotation matrix, I know AXB, AYB, AZB, these are numbers, so I can draw these three unit vectors XB, YB, ZB, and hence it gives you the orientation of the rigid body B in A. Okay, so the rotation matrix containing the column vectors AXB, AYB, AZB completely describes the orientation of rigid body with respect to the A coordinate system. The vector P, if it is fixed in the B coordinate system, can be described in the A coordinate system just by this simple pre-multiplication by a rotation matrix. Everybody knows this. We have seen this in many places in mechanics. So the rotation matrix, one of the property is that it converts a vector in one coordinate system into another coordinate system. A vector in the B coordinate system, PB, can be described in the A coordinate system by pre-multiplying by the rotation matrix. The other important property of this ABR, this rotation matrix, is that it is orthonormal. Okay, so what is an orthonormal matrix? The column vectors are all unit vectors. Okay, so the magnitude of the column vectors is 1, and the two column vectors AXB and AYB, likewise AYB and AZB, and likewise AZB and AXB are perpendicular to each other. Okay, so we have three constraints here. So R11 square plus R21 square plus R31 square, which are the column which represents the column vector AXB, is equal to 1. Okay, it's a unit vector. Likewise, AXB is perpendicular to AYB. So we have 6 constraint equations, 3 unit vector constraint equations and 3 perpendicular constraint equations. So hence, out of the 9 Rij's, only 3 are independent. Okay, so this is a very important result, that in a rotation matrix, there are only 3 independent parameters. So remember, rotation matrix represents the orientation of a rigid body in the A coordinate system. A rotation matrix has 3 independent parameters. Hence, the orientation of a rigid body in 3D space can be represented by 3 independent parameters. Okay, so let's continue. This ABR is orthonormal. We can also, because of this property, determinant of ABR is always +1. Okay, secondly, we know ABR inverse is into ABR will be identity matrix. However, if ABR is orthonormal, the inverse is the same as the transpose. Okay, so ABR transpose ABR will be identity matrix. Okay, or the inverse is the same as the transpose. And what is ABR inverse? Conceptually, ABR was the orientation of B with respect to A. Okay, ABR inverse is nothing but the orientation of A with respect to B. Okay, that is what this means by ABR inverse. Let's continue. This ABR is a 3x3 matrix. Okay, so if it is a 3x3 matrix, it must have 3 eigenvalues. You can show that the eigenvalues are +1 and e to the power i5, where I is this imaginary number, square root of -1. So what is e to the power i5? We can expand it as cos phi plus minus I sin phi. Okay, so this matrix has 1 real and 2 imaginary eigenvalues. where this phi can be obtained as cos inverse of R11 plus R22 plus R33 minus 1 divided by 2. So this will be a homework problem. You can derive and show that the three eigenvalues are 1, e to the power plus minus I phi, and where phi is given by this expression. Now, corresponding to this real eigenvalue 1, we can also find an eigenvector. Okay, so the eigenvector is given by k, which is 1 by 2 sine phi into this column vector. So the first element of the column vector is R32 minus R23. Okay, the second element is R13 minus R31, and the third element is R21 minus R22. Okay, so as long as phi is not 0 or n pi, okay, where n is some natural number, we are not dividing by 0, and we can determine this k vector. Okay, if phi is 0 or 2n pi, then actually there is no rotation. So there is no notion of a rotation matrix, and hence there is no notion of k. Okay, if phi is 2n minus 1 pi, then we need to worry about it a little bit. Okay, if phi is 2n minus pi, then you can show that there are three real eigenvalues. Okay, the next important property of this axis k, this eigenvector k, is that this axis k is fixed in A and B. Okay, how do we prove this? We have a vector k in the B coordinate system. If we pre-multiply by ABR, we'll get the vector in the A coordinate system, just like any other property of a rotation matrix. It transforms the BK into AK. Now, if you look at the right hand side, ABR into BK is also equal to 1 into BK. This is the eigenvalue problem. So hence, AK is same as BK. Okay. So this follows from the definition of an eigenvector and also for the definition of transformation of vector from B to A. Okay, so what does this mean? It means that this eigenvector, which we have found out k, is same either in the A coordinate system or B coordinate system. Okay, so hence when I orient the object or rotate the object from A to B, there is a vector k which is remaining fixed. Okay, and that is what was shown in the original figure here, that whenever you have an A coordinate system and a B coordinate system, we can have a vector k which will take this A coordinate system to the B coordinate system. So what do we have to do? We have to rotate about this k axis by an angle phi. Okay, so this axis k is fixed in both A and the B coordinate system. Okay, so we can find k and phi given the rotation matrix ABR. Okay, so k is the eigenvector corresponding to the real eigenvalue 1, and phi is this expression which is cos inverse of R11 plus R22 plus R33 minus 1 divided by 2. Okay, so phi and k can be obtained from the elements Rij of this rotation matrix. Can we do the opposite? Yes. So it turns out that if I give you k and phi, k as a unit vector, meaning kx squared plus ky squared plus kz squared is 1, and an angle phi, okay, can I find the elements of the rotation matrix? Yes. So R11 is given as kx squared 1 minus cos phi plus cos phi. So for example, R21 is kx ky 1 minus cos phi plus kz sin phi, and so on. So this will also be a homework problem which you can attempt yourself and derive this. So what have we done? Given a rotation matrix, I can find k and phi. Given k and phi, I can find the rotation matrix, elements of the rotation matrix. There is also a very useful notion of or extension or use of k and phi. Okay, so this is let's consider a rigid body B, and the rotation axis K is parallel to the XA axis. So both XA and XB are at the same place. So that is the fixed axis. So now if I rotate about this XA or XB axis by phi, I can find the rotation matrix by substituting in this previous expression. Kx is 1, Ky is 0, and Kz is 0, and rotation angle is phi. Okay, if you substitute Kx as 1, so what is R11? We will get 1. Okay, 1 minus cos phi plus cos phi. What is R23? Ky, Kz is 0. So we will be left with sin phi. Kx is 1. Okay, minus sin phi. So we have 1, 0, 0, 1, 0, 0, cos phi minus sin phi, cos phi. Okay, so this is the rotation matrix obtained when the fixed axis is along the x-axis. So we are going to use this symbol, rotation about x by an angle phi will give a rotation matrix ABR, which is 1, 0, 0, 1, 0, 0, cos phi minus sin phi, cos phi. Okay, and this is what is shown in this figure. So basically XA and XB are at the same place. This is the K axis. We are rotating by an angle phi about this axis. So YA will go to YB, ZA will go to ZB. And the angle between YA and YB is this angle phi. Okay. The rotation about Y and Z axis can also be similarly obtained. All we need to do in that general expressions for Rij as a function of Kx, Ky, Kz and phi, we have to say now that the K axis is 0, 1, 0. For Z, the K axis is 0, 0, 1. And we can obtain cos phi 0, sin phi 0, 1, 0 and so on. Similarly for the Z, the last column will be 0, 0, 1. Last row will be 0, 0, 1. And this is cos phi minus sin phi, cos phi. Okay, so you may have seen this rotation matrices when we rotate about x, y and z axis. So these rotation matrices are called simple rotations because they are the simplest possible rotations. Okay, we are rotating about the x-axis, y-axis and z-axis. Now let's look at one more important concept, okay, which is of two successive rotations. So what do we mean by two successive rotations? So initially we have a rigid body B which is coincident with the A coordinate system. Okay, so the first rotation is relative to A. Okay, so after the first rotation, the coordinate system A goes to B1. The second rotation is relative to B1, the new coordinate system B1, not with respect to the original A coordinate system. So after the second rotation, B1 goes to B. Okay, as is shown here, we have XA, YA, ZA. The first rotation, it goes to XB1, YB1, ZB1. And after the second rotation, which is with respect to XB1, YB1, ZB1, we get XB, YB, ZB. So the question is, what is the resultant rotation after these two successive rotations? Okay, so the answer is ABR is AB1R into B1BR. Okay, so we multiply the rotation matrices in the order of the two successive rotations. That is important. And this is true whenever we are rotating about axis fixed to the moving rigid body. Here we are rotating about axes which are fixed to the moving body. It is about the moved coordinate system, the second rotation. Okay, generalizing, we can also show that the resultant of n such successive rotations about axis fixed to the moving body is product of multiplications of matrices A, B1R, B1, B2R all the way to Bn minus Br. Okay. So again, just to stress, the matrix multiplication is non-commutative in general. So ABR is AB1R into B1BR. It is not B1BR into AB1R. So if you switch the order, then you don't get the correct rotation matrix. And in our notation, where we have leading superscript A, which represents the reference coordinate system, and B, which is the final orientation of the rigid body, the final coordinate system, we can see that this B1 and B1 will cancel, intermediate coordinate system, and we are left with ABR. This is just a way to remember what we are doing. Okay, so in summary, the order of the rotation is important. So we will multiply the rotation matrix in the order of the rotations. So now we can have enough material to look at orientation in terms of 3 angles. Okay, we have the tools and techniques to describe orientation of a rigid body in terms of 3 angles. So we know that orientation is described by 3 independent parameters. Okay, remember in Rij there were 9 Rijs, but then there were the 6 constraints. So there are actually only 3 independent parameters. Okay, so can we obtain the rotation matrix in terms of 3 independent parameters? Okay, so answer is yes. We can do 3 successive rotations about axis fixed to the moving body. Okay, so we can have rotations about x, y, z, and since the order of multiplication is important, we could have got another rotation matrix if we did x, z, y, okay, or y, z, x. So there are 6 different possible combinations of rotations about 3 distinct axes. We can also represent the orientation of a rigid body by rotation about 2 distinct axes. There are also 6 combinations. So we can do first a rotation about x, then a rotation about y, and then again a rotation about x. Okay, we could have also done z, y, z, or z, x, z. So there are 12 possible combinations of rotations about 3 axes. In one case 3 distinct axes, and one case 2 distinct axes. Okay, and we'll get 3 parameters in each one of them. Okay, so these 3 rotations completely describe the orientation of the rigid body. We can also do rotations about axis fixed in space. We are not going to discuss it, but we can see that there are 12 possible combinations for 3 and 2 distinct axes where we rotate about the original fixed axis in space, the XA, YA, and ZA axis. So as you can see, we have exactly 3 rotations: theta 1 about x, theta 2 about y, and theta 3 about z, or some 3 angles about, say, let's say 2 axes, x, y, and x, and we can describe the orientation of the rigid body. So this is the minimal representation of orientation of a rigid body. Only 3 parameters, 3 angles, and no constraints are used. Okay, so historically, 3 angles about 2 distinct axes are called classical Euler angles. Okay, and about 3 distinct axes are also called Tate-Bryan angles. In many textbooks, all of these are called Euler angles. Okay, so this minimal representation of orientation using 3 successive rotations are these 3 Euler angles. So let's take an example. If you have x, y, z Euler angles, what does it mean? We are first going to rotate about x, then we are going to rotate about the moved y, and then third we are going to rotate about the moved z. Okay, so the rotation about x is AB1R. This is rotation of x by an angle theta 1. We can find this rotation matrix. It is a simple rotation about by theta 1 about the x-axis. So you will get 1, 0, 0, 1, 0, 0 cos theta minus sine theta 1, cos theta 1. So what is happening in this figure here? So we have XA and XB1 aligned. YA will go to YB1, ZA will go to ZB1. Okay, and the rotation is angle theta 1. The second rotation is about the moved y-axis. So what do we mean by the moved y-axis? About YB1. So YB1 and YB2 are at the same place. So ZB1 will go to ZB2 and XB1 will go to XB2. So this is the B2 coordinate system. We are discussing orientation and rotation. So the origins of all the coordinate systems are at the same place. Okay. So the second rotation is about y-axis by theta2. So we can again get this rotation matrix, which will be cos theta 2 0 sin theta 2 0 1 0 minus sin theta 2 0 cos theta 2. Okay, the third rotation is about the moved z-axis. That's why it is called xyz Euler angles. So pictorially, what is happening? So if you can see that the third rotation is ZB2. So ZB2 and ZB are at the same place. We are rotating by an angle theta 3. So hence XB2 will go to XB, YB2 will go to YB. Okay, YB1 and B2 are at the same place. So, and ZB and ZB2 are at the same place. So the final coordinate system is XB, YB, ZB. Okay, and the rotation matrix obtained by rotating about the z-axis, which will take from B2 to B, is given by cos theta 3 minus sin theta 3 0, sin theta 3 cos theta 3 0, 0 0 1. So what is the resultant rotation from A to B, which is the product of the three rotation matrices in the order that we did the rotation. So we went from A to B1, B1 to B2, B2 to B. So again, in our notation, you can see that this B1 and B1 sort of cancels out in your head. B2 and B2 will also cancels out, and we are left with A and B. So if we multiply these three rotation matrices, we will get the rotation matrix which contains theta 1, theta 2, and theta 3. Okay, so in this matrix, C2 means cos theta 2, C3 means cos theta 3, short form. S1 means sin theta 1. So Ci and Si denote cos theta I and sin theta I respectively. So this matrix C2, C3 minus C2, S3, S2 minus S1, C2, C1, C2, etc. gives the rotation matrix which describes the orientation of B with respect to A obtained after three Euler angle rotations, and that too about X, Y, and Z axis. Okay, so if you were to do X, Y, X or Z, Y, X, some other sequence, then the rotation matrix will be different. Okay, because why? Matrix multiplication is not commutative. Okay. So I have shown you that if I tell you what is the sequence of rotation about X, Y, Z, and rotation is theta 1, theta 2, theta 3 about this X, Y, and Z axis, I can find the rotation matrix. Can I do the reverse? Yes. So if I give you a rotation matrix with numbers, okay, A, B, R, following the properties of the rotation matrix, meaning unit vectors and orthogonality and so on, can I find the XYZ Euler angles? Okay, the answer is yes. So how do we do that? We look at this rotation matrix which we have obtained for XYZ Euler angles. So you can see here this term R13 is sine theta 2. Okay, so if I give you some number, so theta 2 is sine inverse of that number. Okay, correct? But instead of doing sine inverse, what we will do is we will look at both of these R11, R12 and R13. So if I take the square of these two and take the square root, okay, we will be left with cos theta 2. So we will have sine theta 2 and cos theta 2, and then we can use something like tan inverse. Okay, so this is what is explained here. So theta 2 is a tan 2 of R13 comma plus minus R11 square plus R12 square. Okay, why do we use a tan 2? Because this function a tan 2 y comma x, it takes the y coordinate and the x coordinate, it gives you the angle in the correct quadrant. Okay, so it is basically doing tan inverse y by x. However, it looks at the sign of y and x. So for example, if this was -1 and -1, okay, then we will get in the third quadrant. But tan inverse y by x of both y and x as -1 will give you still 45 degrees. So it will give you the angle in the correct quadrant. So once we know theta 2, let's go back and see. So now I know theta 2. So I can take these two terms, which is r23 and r33, divide by cos theta 2, and I can again do a tan 2 of this term and this term. So this is a minus sign, so we will take care of the minus sign. Okay, so a tan 2 of r23 and r33, of course, with a minus sign. Okay, so that's what is shown here. Theta 1 is a tan 2 minus r23 divided by cos theta 2, r33 divided by cos theta 2. And likewise, we can, theta 2 is known, we can now find theta 3 using again a tan 2 of these two terms, r11 and r12. Okay, which is what is exactly shown here, minus r12 divided by cos theta 2, r11 cos theta 2. Now there is a small problem, which is that if this r13 is plus minus 1, meaning what? Theta 2 is plus minus pi by 2. Okay, so if theta 2 is plus minus pi by 2, cos theta 2 will be 0, and we cannot divide this term by cos theta 2, which is what we were doing. We cannot divide both of these terms by cos theta 2. Okay, so if r13 is 1, which is theta 2 is pi by 2, then we can just do a tan 2 r21 r22. Okay, what do? We look at these two terms, this one and this one, this one and this one. Okay, so if theta 2 is pi by 2, you can see that this is sine theta 1 plus theta 3 and cos theta 1 plus theta 3 we will get. Okay, so we assume or make a convention that theta 3 is 0 and theta 1 is a tan 2 of r21 comma r22. If r13 were minus 1, then we have to suitably change. So theta 1 is minus a tan 2 r21 r22. Theta 2 is still minus pi by 2 and theta 3 is 0. Okay. So what does this algorithm tell you? That there are two sets of values of theta 1, theta 2, theta 3 for a given ABR. Okay, if theta 2 is plus minus pi by 2, theta 1 and theta 3 is not unique. We can only find theta 1 plus minus theta 3. Okay, we make the convention that in either case theta 3 is assumed to be 0 and we obtained a unique theta 1. These condition theta 2 is plus minus pi by 2 are called singularities. Okay, so there always are singularities in any representation where we cannot find the angles uniquely. Let's look at another Euler angle, which is the ZYZ Euler angles. So in this case, what is happening? The first rotation is about Z-axis. So ZA and ZB1 are at the same place. XA goes to XB1, YA goes to YB1, and the rotation is theta 1. The next rotation is about Y-axis. So if I rotate about the moved Y-axis, which is YB1 and YB2 are at the same place, the rotation is theta 2. The Z-axis will go to ZB2 and X-axis XB1 will go to XB2. And the last rotation is about the Z-axis of the moved coordinate system again. So ZB2 and ZB are at the same place. So this is the rotation by theta 3. So now XB2 will go to XB and YB2 will go to YB and ZB remains same. So after these three successive rotations, the A coordinate system will go to B coordinate system, which is XB, YB, ZB. Okay, and what is the resultant rotation matrix? Which is nothing but multiplication of three simple rotations about Z, Y, and Z Euler angles. Okay, so we will get some terms which are C1, C2, C3 minus S1, S3, and so on. The R33 term will be C2. Okay, why are we looking at ZYZ Euler angles? We'll see later that this occurs in many manipulators where we have intersecting rest. Okay, the last three joint axes in a robot are intersecting. That is called as an intersecting rest, and that can be very easily modeled by ZYZ Euler angles. Okay, so what have we done? We have shown that if you rotate about Z, Y, Z by theta 1, theta 2, theta 3 respectively, I can obtain a rotation matrix of this form. Okay, so R33 again is C2. So if I give you some number here, okay, so what is that theta 2? That is cosine inverse of that number. Okay. Likewise, once I know theta 2, I can divide these two expressions by sine theta 2 and do a tan 2 and find theta 1. Likewise, I can divide by here and find a tan 2 and find theta 3. So that is the basic idea, very similar to what we have done before. So we can find an algorithm that if I give you Rij's, what are the ZYZ Euler angles? So if R33 is not equal to plus minus 1, so cos theta 2 is not equal to 0 or 180, then theta 2 is a tan 2 square root of R31 square plus R32 square comma R33. Is that correct? Yes, because I can take the square of these two and we will be left with sine theta 2 plus minus because square root is there, and we will get cos theta 2, and hence we can find theta 2. We can then divide by sine theta 2, this R23 and R13, and find theta 1, and then we can divide R32 by sine theta 2 and minus R31 by sine theta 2 and find theta 3. So given Rij, the elements of this rotation matrix, I can find theta 2, theta 1, theta 3 if R33 is not equal to plus minus 1. Again, if R33 is equal to 1 or minus 1, I cannot divide these quantities. So sine theta 2 will be 0. So again, we have a convention which says theta 1, theta 2 is equal to 0 when R33 is equal to 1, and theta 3 is a tan 2 minus R12, R11. If R33 is minus 1, we have a convention that theta 1 is 0, theta 2 is pi, and theta 3 is a tan 2 R12 minus R11. Okay, so again, given a rotation matrix Rij, we can get two possible sets of ZYZ Euler angles. These two possible sets comes from here, plus minus. Okay, and if R33 is plus minus 1, we have a singularity. Only theta 1 plus minus theta 3 can be found, and for unique theta 1 and theta 3, we choose theta 1 to be 0. Okay, this is by convention. Okay, now let's look at some other representation of orientation. So I have shown you rotation matrix with Rij, I have shown you k and phi, and I have shown you Euler angles, three Euler angles. We can also have something called as a Euler parameter. Okay, we can look at these books by Kane and McCarthy. So these are four parameters which are derived from k and phi. They are not exactly equal to k and phi. The three parameters are k into sine phi by 2, and the fourth parameter is cos phi by 2. Okay, we still have one constraint, epsilon 1 square plus 2 square plus 3 square plus 4 square is 1. So epsilon here is a vector with epsilon 1, epsilon 2, epsilon 3. The epsilon 1, 2 and 3 are called and 4 are called the Euler parameters. They are derived from k and phi, but not exactly same as k and phi. And it turns out to have some small advantage because it is sine phi by 2. So we don't have problems of pi basically. Okay, so if angle phi is pi, sine phi by 2 is still well defined. It is 1, and we can define and derive and various things with phi as pi. We can also have something called Quaternions. Okay, you can look at this book by Afkin. This is also 4 parameters. Okay, these are typically labeled as q1, q2, q3, which is a vector, and a scalar q0. Okay, so it's in some sense sum of a scalar and a vector. Okay, so it is neither a scalar or a vector, but it is often written as Q0 plus Q1i plus Q2j plus Q3k, where I, j, and k are the unit vectors along the x, y, and z axis. Okay, so it turns out that if you have two quaternions, Q1 and Q2, the product of two quaternions is also a quaternion. The inverse of a quaternion also exists. Okay, and the square of Q0, sum of the squares of Q0, Q1, Q2, Q3, so Q0 squared, Q1 squared, Q2 squared plus Q3 squared is 1. Okay, and this is called as a unit quaternion. And unit quaternion represents the orientation of a rigid body in 3D space. Okay, so there are certain advantages in using a quaternion. Specifically, this is extensively used in spacecraft dynamics. Okay, orientation of a spacecraft when it is orbiting the Earth or some other place. The Euler parameters are also used extensively in motion planning. We will see later. Okay, they have certain advantages of relating Euler parameters and angular velocities. So in summary, the orientation of a rigid body is specified by three independent parameters in 3D space. There are various representations of orientation with their own advantages and disadvantages. Okay, so the rotation matrix APR contains 9 RIJs plus 6 constraints. Okay, so it is not really useful to carry along 9 variables and 6 constraints for any computation work, but it is ideal for analysis. Okay, we can also have access kx, ky, kz components and angle phi. So this is a 4-parameter representation of orientation with one constraint. The kx square plus ky square plus kz square is 1. K is a unit vector. This is very useful for insight and extension to screws, twists, and wrenches. So as I showed you, you can think of rotating a rigid body from A coordinate system to a B coordinate system by rotating about this K axis by an angle phi. Okay, and later on we'll see that this can be extended to rotation and translation. We can also have Euler angles, which are 3 parameters and 0 constraints. Okay, so this is a minimal representation of orientation. However, it suffers from the problem of singularities. So any set of 3 Euler angles will have these singular configurations, singularities. More so, we also need to know what is the sequence of rotation. So you have to tell me whether it is XYZ or ZYX or XZY, because every time we will get different rotation matrices. Finally, we had Euler parameters and quaternions. These are also 4 parameters plus 1 constraint. They are similar but not exactly same as K and phi. There are no singularities and it's often used in motion planning. Finally, we can convert one representation of orientation to any other representation of orientation for regular cases. So if there are no problems like singularities and so on. Okay. So once we have a representation of orientation of a rigid body, now let us look at combined translation and orientation of a rigid body. So what do we have? We have this rigid body B with a coordinate system xb, yb, zb and an origin OB. We have a reference coordinate system xa, ya, za with an origin OA and labeled A, and this is labeled B. So the origins of A and B, OA and OB are not coincident anymore because we are also looking at translation. When we were looking at orientation, OA and OB were at the same place. So what is given? The orientation of B with respect to A, this rotation matrix is known or can be obtained. If you take a look at a point on this rigid body given by BP, we can describe this point in the A coordinate system by this simple vector addition. So AP, which is this vector, is nothing but AOB, the vector from origin OA to OB, plus this vector, but pre-multiplied by a rotation matrix. Because this vector is described in the B coordinate system, we cannot add two vectors in two different coordinate system. But fortunately, we can just pre-multiply by a rotation matrix and get this vector in the A coordinate system, and then we can add. Okay, so as mentioned, AOB locates the origin OB with respect to OA. So this is a general transformation which consists of a rotation ABR and a translation AOB. Okay. So from this we can look at this very important concept called homogeneous transformation. Okay. So we have combined translation and orientation. Okay, it's a vector equation, but let's see if we can write it in a more compact form. And what do? We define a new vector A capital P, which is A small p, and we concatenate with 1. So A small p was a 3 by 1 column vector. We add one more row of 1, so it becomes a 4 by 1 column vector. Likewise, B of P, capital P, is BP small p, and we have another row which is 1. This A capital P and B capital P are called 4 by 1 homogeneous coordinates. Okay, strictly speaking, in this, instead of 1, if it was some other variable called W, so we have X, Y, Z for the top 3 and W, then it is homogeneous, but W could be equal to 1. Okay, which is what we do in robotics. So we can rewrite this vector equation AP is equal to AOB plus ABR into BP by adding one more equation, which is obviously true, which is 1 equals 1. And then we have A capital P is some matrix into B capital P. And what is this matrix? The top 3 by 3 is the rotation matrix. The last column is AOB and the last row is 0, 0, 0, 1. So if you expand this, you can show that this equation and this equation are exactly the same. So this 4 by 4 matrix is labeled as T, and this is called as the 4 by 4 homogeneous transformation matrix. Okay, so this is a very important matrix in robotics. It is also a very important matrix in many other fields. So for example, in computer graphics and computer vision, the last row is not 0, 0, 0, 1. If you put some numbers here, the last row can be used to show perspective. Okay, and if you don't use 1, but you use some numbers along the diagonal and this point on this 4, 4 element also, we can represent scaling. Okay, so what is perspective? Everybody knows. So when you look at two parallel lines, it looks like as if it is meeting at infinity. That is the perspective effect. And you can show perspective, or you can implement perspective and scaling by changing the last row. Okay, so in robotics, the top 3 by 3 ABR is the rotation matrix, AOB is the translation. If the top 3 by 3 matrix, submatrix, is identity, then we have pure translation. Okay, if AOB is 0 and we have something here, then it is pure rotation. Okay, so this transformation matrix contains pure translation, pure rotation, and by suitable modification of the last row can be also shown to contain the effect of perspective and scaling. Let's look at some of the properties of this 4 by 4 homogeneous transformation matrix. So first thing is the inverse of AB transpose, which is denoted by ABT inverse, can be obtained in closed form. I don't need to use brute force elimination for this 4 by 4 transformation matrix. The top rotation matrix in this ABT inverse is the transpose of the rotation matrix, and the last column is minus ABR transpose AOB. Okay, so this will be a homework problem. You can show that the inverse of the 4 by 4 homogeneous matrix can be easily obtained. You can have two successive transformations. We can go from A to B, B1 to B. So in this case, what is the transformations? It is both translation and rotation. Okay. So then the resultant transformation ABT is nothing but the product of these two homogeneous transformation matrices. So AB1T, B1BT. Moreover, okay, we can have closed form expressions for this resultant successive transformations. Okay, so the rotation matrix on the top is nothing but the product of the two successive rotation matrices. And the translation is again basically summation of two vectors in proper coordinate system. So B1 OB plus AOB1, but B1 OB cannot be directly added to AOB1. We pre-multiply by ABR and then we can add. So likewise, if you have n successive transformations, A to B1, B1 to B2, finally Bn minus 1 to B, the resultant transformation is nothing but the product of the 4x4 homogeneous transformation matrices in the order of the transformations, in order of the translation and orientations that you have done. Let's continue. The transformation matrix is a 4x4 transform matrix. Okay, it is of dimension 4x4. So clearly there must be 4 eigenvalues. So it turns out that the eigenvalues are plus 1 repeated eigenvalues and e to the power plus minus I phi. So e to the power plus minus I phi is cos phi plus minus I sin phi. And what is phi? It is the same as what we obtained for the rotation matrix. So it is some cos inverse of the trace of matrix and so on. Okay, minus 1 divided by 2. So the eigenvectors corresponding to plus 1 and plus 1 is only 1. This is very interesting property. So we have 2 repeated eigenvalues, but there is only one k, one axis of rotation. There is no other eigenvector. Okay. ABT, this homogeneous transformation matrix, represents the general motion of a rigid body in 3D space. Okay, why? Because it contains both the translation, remember AOB, and the rotation. So it contains all the 6 parameters which are 6 degrees of freedom of the rigid body in 3D space. So we should be able to figure out what are the 6 parameters in this ABT transformation matrix. Okay, and the answer is reasonably interesting, that we can show that the general motion of a rigid body can be represented as a twist. What is a twist? It is a rotation about a line and translation along the line. So the direction of the line is this kx, ky, kz, the axis. The location of the line in 3D space can be shown to be derived from k and some y cross k vector. Okay, so where y is obtained from the identity matrix, transpose of the rotation matrix, the translation, and 2 into 1 minus cos phi. Okay, division. So there are 4 independent parameters in k and y cross k. Why? There are 2 in this k, it's a unit vector, and y cross k is perpendicular to k. Okay, so k dot y cross k is equal to 0. Okay, so there are 4 independent parameters in the location of a line. A line in 3D space is located by 4 independent parameters, if you think about it. So we can have y equals m1x plus b1 and z is equal to m2x plus b2. So m1, m2, b1, b2. 4 independent parameters describe a line in 3D space. And a nice way is to show in terms of k and y cross k. Okay. The last 2 independent parameters are rotation of the angle phi, which is also an independent parameters, and the translation along the line, which is AOB dot k. So there are 6 independent parameters here, 4 in the line, 1 rotation, and 1 translation. Okay, so you can look at more details about twists, eigenvalues, and eigenvectors in several papers. We can look at a paper which we published in 2006. So in summary, we first need to define a right-handed coordinate system x, y, and z, which is the reference coordinate system, to represent a rigid body in 3D space. So coordinate system means x, y, z, and an origin OA. Okay, we are going to label all these coordinate systems with A, B, C, etc. because there will be many such coordinate systems. A rigid body in 3D space has 6 degrees of freedom with respect to another rigid body A. So 3 for position and 3 for orientation. So the rigid body B is basically conceptually identical to a coordinate system B. Okay. We are not really interested in the shape and size and weight and other properties of the rigid body at this stage. So the position of a rigid body is nothing but the position of a point of interest on the rigid body with respect to the coordinate system A. So these are most of the time represented by 3 Cartesian coordinates px, py, pz, which are nothing but the projections of this vector AP from the origin of the reference coordinate system to the point and projecting this vector along x, y, and z axis. The orientation of a rigid body can be described in many ways. First, a 3x3 rotation matrix. Second, angle phi and k, or the angle axis form. We can also describe using 3 Euler parameters and finally using 3 Euler angles, and we can finally describe using Euler parameters and Quaternions. There are algorithms available to convert one representation to another. If you combine both the translation and orientation, or position and orientation of a rigid body, they can be combined in this 4x4 homogeneous transformation matrix, which represents the position and orientation in a compact manner. Okay, and as shown last slide, that the properties of ABT can be related to a screw, basically a line about which this rigid body rotates and about which it translates. Okay, so with this, we'll come to an end of this first lecture. In the next lecture, we'll look at how to represent the elements of a robot, basically the joints and links which make up the robot.